Hello everyone, hope all is well today. My name is Gilamat. Today we'll discuss assessing normality with the use of a quanta plot or a normal probability plot with R. Here in my editor, I'm going to build three numerical vectors. I'm going to call them x, y, and w. This is done with the C function, which combines values together. And so I'll select my commands to build my three numerical vectors and then submit them to the console with the prompt by using a Control R, or if you're using a Mac, it's Command Enter. I'm on Windows, so it's Control R. And so now I build X, Y, and W. Let's say that I start with Y, so I want to build a QQ plot for Y. I want to know if it's reasonable to assume that this is a random sample from a normal population. So I use QQ norm of Y. This will build the quanta plot. Just to explain a bit what R is doing to build the plot. So on the vertical axis, this is sample quantile. So these are actually just the values that we observe. And so, for example, if I look at the summary of Y, and so the minimum is 6.1, so this is the first value here. Maximum is 12.6, so 12.6, this is the largest value here. And then the median is 9.6, so about half of the data is found under 9.6. Okay, and then what we're going to do is from the sample quantiles get the theoretical quantiles. These are Z values that correspond to the different percentile ranks. And so, for example, at the median, which is 9.6, this is a percentile rank of 50%. And so I want to get the Z value that corresponds, or the quantile from a standard normal distribution that corresponds to 50%, which would be 0. And so 9.6, which is around here, should correspond to about 0. Okay, and then if we look at the first quartile, which represents about 25% of the data, this is around 8.9. So at around 8.9, we should have a correspondence of the first quartile for a standard normal distribution. So what is that? So if I do Q norm, and I want to get the 25th percentile, so I use 0.25. Mean is 0, standard deviation of 1, I see minus 0.67. So the 8.6 should correspond to around minus 0.67. We see this it corresponds well, and so on. Okay, so this is how the plot is built. And then if we do have a sample from a normal population, we would expect to see a linear tendency in our plot. Now, to help us to see this linear tendency, of course, the quantiles, the sample quantiles and theoretical quantiles are not on the same scale. They don't have the same center. And so what we need to do is think in terms of the proper line here to make the correspondence. And so the appropriate line is going to be a line where I'm going to use a function called AB line. The first argument is going to be the intercept. The intercept will be the mean of our variable, and then we have the standard deviation of our variable, which is the second argument for the slope. So the intercept is the mean, the slope is the standard deviation. I add this line, and this will help me to assess if I have a linear tendency. Okay, so with linear tendency in a plot, it would be reasonable here to assume that we have a random sample from a normal population. Okay. Now, let's look at the other two variables for x. So I do QQ norm of x, and then I'm going to add the line where the intercept is the mean and the slope is the standard deviation. And then here we see that actually we're not following the expected line, and so it would not be reasonable to assume that we have a sample from a normal population. Okay, so here actually the tendency is way off, and then there are some outliers which are pulling our tendency away from the expected line. So it would not be reasonable to assume that this is a sample from a normal population. And then let's look at W. So, oops, so I do QQ norm of W, and then I'll add the line. So intercept again is the mean, standard deviation is the slope. And here we see a curvilinear tendency, and so again this would mean that we have proof against a normality. So it would not be reasonable to assume that your sample is from a normal population. For example, here, if I look at the histogram of W, here we actually see a very strong skew. So it's strongly skewed to the right, actually. And so it's not reasonable to assume that we have a normal population, or that it's a sample from a normal population. Okay. I'll end the discussion with an example where we have data stored in a file. So I'm going to create a data frame called data, use the function called read table, file.choose as the first argument, header equal to true because I have names of columns in my file, sep equal to /t because I'm going to use tabs to separate my columns, and then R is going to ask me where is this file, and I put it in my documents, and I'm going to try to find the file. Let's use methadone. Okay, so I created a data frame. I'm going to get the names of my columns with the function called names. And then here I see actually 3 columns. The first column is just an identifier for my patients. And then each patient were given for a certain amount of time. These are patients that suffer from chronic disease, chronic pain. And we want to know if methadone is going to help them reduce the pain. For a certain amount of time, they were given a placebo. And then for a certain amount of time, they're also given a methadone. And then we have scores of pain under the placebo, scores of pain under the methadone. And so for each patient, what I'm going to do is I'm going to compute the difference of the 2 scores. So I'm going to create a function called a vector called d, and it's going to take the pain of score under the placebo. So I take my data frame, $, and then the name of my column. So data $placebo. This is for each patient. I have the pain score under the placebo. And then I'll do the same for methadone. So data $methadone is the pain score under methadone. So now for each patient, I'm going to have the difference of the pain score between the placebo and the methadone. And I would like to know, is it reasonable to assume that this difference comes from a normal population? Okay, so I'll do QQ norm of D, and then I'll add the line. So AB line, the mean of these differences and standard deviation of these differences will give us the intercept and the slope respectively. And then I look here, I see actually a linear tendency in my plot. So it's actually reasonable to assume that these differences come from a normal population. Okay, so this is how you construct QQ plots. I'll show you how to build normal probability plots. By default, R does not do this. So we defined a function in a file called plots.r. So I'm going to source the file with the command source. So I'll do file.choose. Okay, and then I'm going to find the file. In my documents, I have a file called plots.r. So I find it. And then in this file, I'm going to have a function which is called ppnorm. So ppnorm. And then if you properly source the file, you'll see the following output. So it says function x, use method ppnorm. This means that we now have access to the function called ppnorm. And so what I'm going to do is put my differences, my vector d, which is the difference between the pain score under placebo minus the pain score under methadone. So I'm going to use pp norm of d. And then this creates a normal probability plot. The information is similar to what is found in a QQ plot, except the sample quantiles are now on the horizontal axis. The vertical axis represents the theoretical quantiles. So these are actually the Z values. But instead of giving a Z value, we give the corresponding probability. So for example, for 0, instead of putting a Z equal to 0, I'm going to say, well, this corresponds to 50%. Okay. And for example, for 95%, this will be 1.65. So instead of having Z equal to 1.65 here, I put 95%. And so when I look at 95%, I should have about 95% of the data that's under this line. Okay, but the information is exactly as a QQ plot. We want to see the linear tendency, And here, actually, the intercept and the slope are a bit different. The slope is actually 1 over the standard deviation, so it still depends on the standard deviation. Okay. Now, let's create the normal probability plot for x, y, and w, as we've seen a while ago. So if I do pp norm of y, which is actually the first one that we saw, and then again we see a linear tendency, and so it would be reasonable to assume that it's a sample from a normal population. If I do pp norm of x, here again we're not following the expected line, so it's not reasonable to assume that we have a sample from a normal population. And then I do pp norm of w, and then again we see curvilinear tendency here, so it's proof against normality. It would not be reasonable to assume that this is a sample from a normal population. Okay, so our functions are called QQ norm, which is builds a normal quanta plot, or we can source the file plots.r, and then we have access to a function called ppnorm, which builds the normal probability plot, which is equivalent to the quanta plot. Okay, and so that's it. Have a good day.